Today we will talk about mill turn, some advanced options, and the great connection that we have between milling and turning operations, because this is the module, mill turn, a combination of milling and turning operations on different tables. And I draw a part for this where I can demonstrate different kinds of operations on different angles. I can work on face and with indexial XY axis or XC axis. I can use I can work on angled faces, indexial. I can rotate and make transform. I can use this part for turning and grooving operations, angle grooving, radial operations, and radial drilling. I can demonstrate on this part almost everything in SolidCAM. Today we talk about the great connection, as I say, between the milling and the turning operation. And this is the easiest way and the best software and easiest software in the market today that combine both milling and turning in a very easy way. So I draw this part, and I have also 3D bodies for stock, for example. Not always you will have the standard situation to define a cylinder stock or to draw a sketch and make a revolved. Sometimes you get a different shape, maybe a stock from that it's already was machined on another machine, and we need we can support any shape and form. Not only the stock, I draw also the fixtures, because if we want a good simulation and a good collision control, collision check, we need to see exactly the situation that we have on the machine, exact fixture and exact stock. For this, I draw also the fixture for main spindle and for sub spindle. Now, let's start to make a new part in mill turn. Yeah, save it. As you know, maybe yes, maybe not, we have also the internal mode today that all CAM data that we define, we save into inside the SolidWorks part or SolidWorks assembly. I will work in internal. It's easier to share the part with other programmers from the same office. You just send the part and it will contain the entire CAM data. You don't need to send the file PRT and the folder and make zip and all this. No, all information is inside the SolidWorks part. So I define it internal. And the first thing that we need to do in SolidCAM is coordinate system, home definition. I select a machine, 2 tables, and an upper turret with B-axis and a lower turret with a type rotary. Mill turn, we define home as center of revolution phase, and I will touch the biggest diameter on the part, and I show you why. Because in the home fields levels for radial, we take these dimensions from the surface that we pick. So if I pick another surface, I will have an incorrect levels. This is the best way to define a home, to pick the largest diameter. SolidCAM, as we define in machine kinematics, if I have 4 sub-machines, SolidCAM will generate automatic 4 coordinate systems. For upper turret on main spindle, I have 1 coordinate system. Upper turret on back spindle, I will have another coordinate system on the back side of the part, and the same for lower turret. 2 coordinate systems for upper, 2 for lower. We also generate today coordinate system in SolidWorks mode. So who wants to use it for measurement or any other thing, you can use it. Who don't, just hide it. Hide. I say hide. Thank you. Save. I define the coordinate system, and now the next step is stock and target. The basic functions is to define the stock as cylinder, or to draw a sketch in plane ZX to be revolved around the axis. Today I will use the option 3D model. Something wrong with my computer? No. Okay, and I am make sure that generate envelope is check it. This is solid. So it can generate envelope now for the stock. We can see it in here. The blue sketch is the generated envelope for the stock and the target. Just click on the target, and also we generate the envelope. Next step will be the setup, where we need to define the position of part in machine space. Also for G limits calculation and for machine simulation. Setup. If you don't have it in operation tree, it's a setting. Generate for me a setup. If you don't have it, add a machine setup with right click. Now, what we have here, a connection between sub-machines and coordinate system. For turret 1, table 1, upper turret for me now on this machine, and main spindle will work on Mach 1 position 1. And here on X, Y, and Z, we will need to define distance where the Mach 1 position 1 is related to submachine. Submachine for me is the face of the spindle, face of the chuck, where the fixture is connected. Now let's define a fixture first. It will be easier to define XYZ dimension after the fixture definition. For fixture definition, we have the standard chuck definition for main or sub, clamping internal or external, and with different points. Selecting clamping diameter, wherever I pick in any point on the part, the red connection point, the red point that we see in the picture will go also for axial position. Here, in any place, easy to set up. But I will use. Also, we have the option user define. You can draw a sketch for the fixture, and the best option that is to use the 3D model is the real one. You can draw exactly the fixture that you have on the machine. Also, I want to generate envelope 1, 2, and 3. This is the fixture for the main spindle, table 1 in our machine. The envelope for the fixture is generated. And we go back to the setup. Now, any submachine that containing the table 1, submachine turret 1 on table 1, and also turret 2 on table 1, will use this clamping fixture. For sub-spindle, the same method. I will use 3D model. And select 1, 2, 3 bodies for back spindle fixture. We have the envelope generated. And now we need to measure and to position the coordinate system Mach 1 position 1 related to the submachine. So let's see, I will use SolidWorks measure option from face of the part to this back side of the fixture. Here, this fixture will be connected to the chuck. So my submachine is on a face of chuck. I have 165.28. And for back spindle, back side of the part to fixture, 161 millimeters, but is negative direction because the submachine for back spindle is have the same direction for coordinate system. Now let's check. Press on I see the fixture defined, and the red point is the submachine. So it's defined correct. Also for the back spindle, you see the fixture, and the red point is here, back side of the fixture, face of back spindle or sub spindle. This is the setup. Now we can start to working. Now I will define first a milling operation to see how we will get the stock updated for turning. This is what I want to show you today, the good connection between milling and turning operation. And in the opposite way, we can define a turning operation and use the rest material, the remain stock, for the milling. Now, I will use for a milling 3D machining, because not only on milling machines we need eye machining, also in mill turn we need eye machining. I will take the test machine next, and let's see what material. I will take a free machining, something not important, only for demonstration. Tool, the default tool for milling, 6 millimeters with or without a holder, and levels from face up to the surface only 30 millimeters. Just make it a little bit rough. And motion control, I don't want to use X and Y axis, because this is standard mode. Any machine can work on with X and Y. Here in mill turn we have many situations that not all machines have Y axis, and we have to use X and C, a rotary axis. So I will select the 4th axis, working polar, and for turning I will check update material boundary. Save and calculate. Take a few seconds to calculate toolpath for 3D machining. It's time to finish. Yes. Now I need to calculate the updated stock and toolpath preview. Let's simulate. Okay, I have a schematic machine only with B-axis upper turret and rotary for lower turret, main spindle and back spindle. You see, because the setup I define 165 millimeters, Mach 1 from the face of the spindle. That means the fixture will be connected here on the face of main spindle. And let's play. Working only X and Z-axis. First step with small back steps, and we had also a second main step with small back steps, and now opening the pocket, inside pocket, and that's all. I'm machining in on Milton. Exit. The material boundary should be updated for the turning. Okay, now we have a green sign on the operation. Add the turning operation on Mach 1 position 1. Define the geometry. You see already the stock what was before, and now after high machining operations the stock is updated from here auto 2 constant Z up to here. Modify geometry. On start you already have an extension, auto extend to stock, and for the end of geometry also I check extend to stock, and the geometry is extended up to the stock. Next step is the tool selection. Composite tool with a shank of 25 millimeters and 150 length. I'm just position the shank on the station Z minus 150 and X 32 plus direction. Want to work in this way. You also can see the tool here and also in the picture. Levels, technology, I want to work rough, smooth, equal steps with adaptive step down 2 millimeters, and I will also add finish as material only with compensation. Save and calculate, and let's see the tool path. Front preview. Yes, the tool path is going to take only the rest material that we have here, a few steps, and here in this area where we don't touch it, we will do the standard rough operation. A very fast and economic toolpath with no air movements. It was fast. Let's make it slower. And finish. This is the connection between milling operation and turning operation. We can update the stock from milling to turning and also turning for milling. Another good option that we have in Milturn, an advanced Milturn today, is to control the machine. We want to work now, we take the part, for example, to the back spindle and work on the other side of the part. For this, we have machine control operation. Okay. Now, what we want to do. This is the tool for the user. Whatever you want to do, you can do it here. Control the machine, control any device just to generate the correct G-code for your program. So for a part transfer with rotation, first of all, we need to make a retract of turret, because turret finish the work here in the clearance plane with the tool, and now if I want to come with the back spindle and catch the part, I need to retract the turret. Retract the turret, just drag and movement, go to reference. Now you will make an interpolated movement to the reference, but I can do it axis by axis. Y I don't need to move because after turning Y is always on 0. I will put here the movement and also B here. I will have three movements, three separate movements, X, Z and Y. Save and calculate. My turret is on retract position. Now the back spindle should be now in turning mode operation. That means C-axis not connected. So table 2, working mode, turning, and also open the chuck for me. Prepare the chuck to catch the part. Clamp, open. Main spindle, table 1. I will activate the synchronization. Now a command. I will synchronize the main spindle with the back spindle and send a rotation command. Now 500 RPM, for example, is enough. When main spindle will start the rotation, also the back spindle will rotate because they are synchronized now. Table 2, start moving to the part. Movement. I can do it in part mode or in machine mode, and I will select this cell editor option. I see here the envelope of fixture for back spindle, and with the mouse wheel we can go forward to the part. Now you can go millimeter by millimeter, or you can press Control and it's going hundreds. Zoom. Also Control and Shift, I will have tenths. This is the position, 1333.7. Now where you can do a rapid movement to the clearance of the part and another movement with feed into the part to catch it in this position. Back spindle, the chuck we need to close, clamp close, and the main spindle chuck will be open. Next, it's a movement of table 2 to reference with the part. I will select part move, go to reference. Don't use C-axis because it's turning, it's not connected. Save and calculate. This is the part transfer process that any user can define in a minute. Let's simulate all these three operations and to check if what we did is correct. I will jump directly to machine control. So we see here after turning operation, tool is in safety point. Now, first movement should be a turret retract in X. After this in Z-axis and B. The same can be done also for lower turret, a retract to a different safety position. Now the back spindle is coming and catch the part. And retract to the reference. The transfer process is done. Now we can add here in machine control something that I forgot. After the back spindle reach the reference point, now table 1, stop the rotation off, and also the synchronization of save. This is for G-code more than for the simulation. Synchronization and rotation. Now I want to show you another great option that we have now, working with a rotary turret with an angle tool. That means if you have a holder, angle head can be fixed, or you can set up the angle. Let's make an operation here on this face. It's on 50 degrees, if I remember. Between this face and this face we have 30 degrees, yes, 50 degrees angle. Now, making a milling operation, a profile on submachine turret to table 2, lower turret on back spindle. Coordinate system Mach 4 position 1 is selected automatically, but I want to make a position now to define a position. Okay, I just pick the face, coordinate positions created. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . and define the geometry. Autoconstanze, yes. Tool. Now let's see. I want to add a tool and mill for turret 2. It's mounted on station 1, and I will add an angle of 50 degrees. Levels, upper level is here and lower level save and calculate. Simulation. An angle head can be used working on rotary turret. Hide the stock. Working on this plane. You can mount the tool in any angle, depend on a part and also the holder that the user have. Another great option in mill turn is working on side. Let's hide this coordinate system. Hide. Working on side radial operations as milling or drilling. Add a milling operation, a profile on Mach 4 position 1 with lower turret on back spindle. What we need to do is only to tell that to define this geometry as wrap around z-axis. We define another tool. This angle tool can be used now because we need a 90 degrees tool to a perpendicular tool to z-axis. Levels, just pick the face and profile depth, pick this face. In motion control, you will see the 4th axis is automatically checked, and you have the option to select between polar and Cartesian coordinate type. Now, not on all machines we have the Cartesian option. It's an option on controllers, but polar, all can use rough coordinates, Z and C-axis movement. Save and calculate. Working with Z and rotation of C-axis of back spindle. You can use also as a pocket with eye machining. Working on wrap is the same as you work on a plane. And also, let's define a drilling, a radial drilling. Define a drill for turret 2. It's automatically mounted on station 3. Drilling. What I select? I select yes, head, drilling, select the turning. We need to define the geometry around 4 axis. Around z-axis, and just pick the face. Click on the face. Automatically SolidCAM will detect drills that intersect the rotation axis. I can pick this face also. Only one drill is selected. Those two, they are not intersect the rotation axis. And here the same, and here. Also, I can select only, delete, let's unselect all, those 3 and this. And you can use transform around 4 axis. I define, oh no, it was not saved, I done a drill on turret 2, levels, upper level, and drill depth. Of course, if the drill depth is different, you'll define 2 different operations. Save and calculate. Transform can be used, as I say. We need to transform this operation 2 times 120 degrees. And the transform 4th axis include the original 120 degrees 2 times. And I have the first one on 0 degrees, 120, 240 degrees. It's rotated correct, yes. 1 drill here, 3 drills here. This is a great connection between milling and turning and MCO. With this combination of milling, turning, and machine control, we can do any part on any machine containing more than 1 turret and more than 1 table or spindle. This is what I have wanted to show you today. This is the version of 2013, Service Pack 4. We don't have any new operations or functions. This is all for today. If you have questions now.
Okay, thank you, Florine. I see we have no questions today, so I want to thank you everyone for joining us, and I hope you will also join us for next week's webinar, same day and same time. So thank you very much, and have a great day.